The limit laws are a group of 4 results that will make our lives a bit easier. In particular, these laws will allow us to take large limits and break them down into their constituent pieces. If we know the limits of each piece, we can then reassemble these pieces to find the limit of the entire function. So let's get to the laws. We begin by supposing that we have two functions f and g. We know that both limits exist, and we know the values of both limits as well. Let's call them L and M. The first limit law is that if we multiply a function by a real number, the result is that real number times the limit. Next up, if we take the limit of a sum or difference, then the result is the sum or difference of the limits. Now the same is true for the products of two functions. The limit of the product is the product of the limits. And finally, if we divide two functions, then we can also divide their limits so long as the denominator is not 0. So these limit laws tell us that we're effectively allowed to do what we want to do, right? To split up limits into their pieces. And we'll see that there is an important caveat, but we'll do that later. First, let's focus on an example. So let f and g be two abstract functions whose limits are known. For f, the limit at 0 is 4, while for g, the limit at 0 is -2. Let's find the limit of f squared plus 2fg at 0. So for this example, I'm going to go into excruciating detail by breaking it into smaller pieces. The first summand is f squared, right? And we know that we can write that as f times f. And now applying the third limit law tells us that we multiply together the limits of f. That gives us 16. Moving on to the second summand, let's start by looking at f times g. Now again, we're going to use the third limit law, which tells us that we can multiply the respective limits, giving us -8. But the second summand also has this factor of 2 in there, so we have to apply the first limit law as well to get the final result of -16. Now putting this all together, we apply the second limit law to write the original limit as the sum of two limits that we've already computed. Plugging in those numbers that we worked out before gives us a final answer conveniently of 0. Now this was a lot of work, and it's not what we do in practice. Rather, we'd begin by looking at the limit and convincing ourselves that the limit laws apply. Then we would systematically use the limit laws to break the original limit into smaller pieces with which we are familiar, like so. Eventually, arriving at a point where we can just substitute our values in and arrive at an answer. Now I mentioned before that there was a caveat in our use of the limit laws, and let's talk about that now. The statement of the limit law theorem requires that we know that both limits exist to begin with. So, if one of the limits does not exist, then the limit laws do not apply. Let's see an example where misapplying the theorem could steer you wrong. Look at the function xe to the 1 over x as x approaches 0. If you try to split this up naively and use the fact that the first limit is 0, you might think that the overall limit is 0, but that turns out not to be correct. In reality, this limit does not exist at all at 0. And we cannot use the limit laws because the second limit, e to the 1 over x, simply doesn't exist. So make sure you're not accidentally misapplying these laws when you start working through limits. Now, a nice corollary to the limit laws is the following. If you are given any polynomial whatsoever and any real number c, then you can evaluate the limit of that polynomial simply by evaluating the polynomial at c. So to see why this is the case, note that the limit of x to the n can be systematically reduced to the limit of x by repeated application of the third limit law. And so, by applying this fact and the limit laws to the entire polynomial, we can evaluate the limit as so. Which just works out to be the value of the polynomial evaluated at c. As an immediate follow-up, let's suppose that we now have two polynomials, p and q, and we know that q of c is not 0. Then the limit of the rational function p of x divided by q of x at the point c is just p of c divided by q of c. Putting this to work, let's find the limit of the following rational function. Let's take p of x to be the numerator and q of x to be the denominator. Plugging -2 into q gives out a non-zero value, so the corollary above applies. And the value of the limit can be determined by plugging 2 into everything. So if we work through this little bit of arithmetic, we eventually arrive at an answer of -13/2. So we've now learned how to break large limits into smaller limits in order to solve them more easily.